Welcome everyone for the 11th lecture of Introduction to Astronomy and Astrophysics course. Today we will start our lecture on the module Galaxy. First, we should recap what we have done till now. So in the first module we had covered the introduction part, that is the first history of astronomy to modern day astronomy. Then we introduced about the solar system object. Those are the planets, different planets, how their composition, how their size varies. We discussed those things. And the next thing we learned about how the distance is measured in astronomy and different distance measurement techniques such as parallax, Cepheid variable, a period luminosity relation, etc. were discussed in this lecture. After that we covered we covered the module M4, just skipping the two other in between modules. In the module 4 we learned about some absorption emission process and recapped our physics lessons. And next we introduced two different kind of telescope and the tools of astronomy and few terms which are very related to observation of astronomical objects were discussed. Also for the M4 we will have another the last class where we will recap the whole M4, but that will be in the list of this course. Then we came to the module 2 and started about discussion of stars. First we discussed our sun, then we discussed about the other stars, different population of stars, how the stars evolve based on their mass. And the next thing we learned about what are the exoplanet, how the exoplanets are detected and why exoplanet is a growing field today. The next module I will cover from today onwards at the galaxies. Today's lecture will be about a 1 hour lecture or 1.5 hour lecture, where I will introduce the galaxy and discuss few key things about galaxies. Then the second lecture and the third lecture will be on the galaxies evolution and our Milky Way galaxy also there will be in the course. From the weekend of this from the weekend classes or from this week we will introduce the Python thing, and also some topics in this galaxies lecture will also have introduction with the Python theme. And in the penultimate lecture maybe we will discuss the history of universe, and this will be a short overview or the outline of the course till now and what we will be discussing in future. So now we can start our lecture. So this is the module 3 lecture 1 and the lecture title is Galaxies. So in the universe there are three ubiquitous structures. Those three structures are atom. Yes. Maybe it is okay now. In the universe there are three ubiquitous structures, such as these three structures are atoms. Those are the smallest structure. The next biggest structure are the stars, and the third or the most biggest structure of the universe are the galaxies. Now if one asks you what is a galaxy, you can tell that galaxies are agglomerations of stars, dust, gas and the dark matter. So galaxies are made with stars, dust, gas and dark matter. Average ratio of gas is to stars is to dark matter is about 1:10:100. But this ratio 1:10:100, this ratio varies depending on what type of galaxies you are studying. But On average, this mass ratio of gas versus stars versus dark matter is 1 is to 10 is to 100. They are the basic building block of the universe on the large scale, you can say. The galaxies show broad range of physical property. You will see in the subsequent slides that the galaxies vary in the with their star formation, vary in their age, vary in their shape, and also vary in their color, and other different properties, physical properties of the galaxies are different based on which class of galaxy you are studying. Understanding of galaxy formation and evolution is one of the main understanding problem of modern cosmology. It is believed that how the universe formed and what galaxies we are seeing today is correlated, and if we can trace the galaxies with the different distance or the different age, then we can learn something of how the universe formed or how the things get formed. It is believed that there are about 10 to the power 11 galaxies in the observable universe. Each galaxy has a typical mass of about 10 to the power 8 to 10 to the power 12 solar mass. So here in the figure there are different kind of galaxies you can see. This figure is zoomed so much. So this is not very good representation of telling what is the shape of the galaxy, but it is a Hubble default image where the different high redshift objects has been given. I will not discuss this figure, but I guess there is a very good figure. You will get some good figure in the subsequent slides. One thing you have to keep in mind that some terms will come from today multiple times, such as when we call the matter, we will just focus on those content of universe. This are sensitive to gravity and electromagnetic force mainly, and the dark matter only sensitive to gravity. It does not have the electromagnetic kind of force. And there is another type of content in universe, that is dark energy, that is not sensitive to gravity or the electromagnetic force. But in the universe you will see the dark energy has the most content is most highest. That is the dark energy is about 73% of the content is dark energy. About 23% of the content is the dark matter, and next 4 to the rest of percentage is made up with the normal matter and the neutrino, which have mass. The next thing we will learn what is the dark matter, what is the ordinary matter, and what is the difference. So dark matter is an invisible substance that make up about 27% of universe mass and influence the formation of galaxies and the large scale cosmic structures. So dark matter is about 23 to 27% substance of the universe, which makes up the galaxy and the cosmic structure. There are different evidence of dark matter, such as those evidence come from the galaxy rotation curve, galaxy cluster collision, cosmic microwave background, gravitational lensing, large scale structure formation, and galaxy's velocity dispersion within cluster. Today's lecture will not be covered any of these topics, but this is just for your reference given. And what is the difference between dark matter and the ordinary matter? Ordinary matter is made of atoms, interacts with light and radiation, whereas the dark matter is made up with unknown particle. Still we have no idea what particle the dark matter is made of. And the detection of dark matter is done via indirectly through the gravitational effect of the galaxies, whereas the ordinary matter detection is done via the light emission and the physical interaction. And the dark matter is the most abundant part of the content, abundant part in the mass energy content. About 27% of universe is made up with the dark matter, whereas for the ordinary matter, only you can say only 5% of the universe total mass is made up with the ordinary matter. Dark matter has a huge role in the formation of galaxies. Dark matter's gravitational pull help to clump ordinary matters together, and this form the scaffolding for the galaxies for the formation and evolution. Dark matter shapes the universe large scale structure also. Here is a brief history of the extragalactic astronomy I will discuss now, and then I will discuss what are the galaxies we are for now. So here is this extragalactic astronomy started, you can say, not in the term of extragalactic astronomy, but in 1755 the Kant gave idea of island universes. He wrote a book called The General Natural History and Theory of Heavens, in which he said that the Milky Way like a huge solar system, rotating and origin from a rotating cloud. Stars fall from the disk plane on different orbits. Disks like Milky Way project to ellipses. Oval nebulae seen by D. Moffatis are called island universes. In 1912, Slipher discovered that the nebulae, that are the bright patchy objects on the sky, are rotating. In 1920, Shapley and the Cutis, two astronomers, made the bet that our spiral nebulae, that the nebulae are those bright patchy objects seen in the night sky, are the island universes. They had a 30-minute debate presentation by each. Shapley, who told that the island universes are within our own Milky Way, won the debate, but being right, Cutis could not win in this debate because there was no direct evidence that this kind of bright nebulae were outside our solar system. So until 1920 there was no idea about extragalactic astronomy. They believed that the bright patchy objects in the night sky are itself within our Milky Way galaxy. In 1925, that is the 100 years before today, the Hubble first discovered Cepheid stars in the Andromeda galaxy, for which the luminosity vary with the time. From that luminosity, using the period luminosity relationship, he measured the distance of the Cepheid star in the Andromeda galaxy, and he found that this distance is very much greater than the size of our Milky Way. So this established that this Cepheid stars, or the star host, or the Andromeda galaxy, is outside our Milky Way. Then this was the first evidence of first introduction of extragalactic astronomy. So extragalactic astronomy or astrophysics is about 100 years old. So from the 1700 itself, the cataloging of nebulae or the bright objects of the sky started. So if you see some objects in the sky, maybe that is stars or galaxies, you first have to catalog those objects. Then you have to make a census of this object, so that you can make a census of the object correctly. And then the next step will be you have to do the classification based on some observable properties of those galaxies. So this nebulae classification or the cataloging thing or making census thing, you can say, was started in early 1700, where Meissner made a catalog of 109 nebulae so that the comet hunters would not miss them for the comets. In 1700, there were around 40 such Messier objects. In 1888, the Dreyer, another astronomer, who introduced another catalog. This is known as the NGC catalog, or the New General Catalog, that had about 8,000 objects. 8,000 objects, of which around 50% were galaxy. Still, the NGC naming convention has been used, and we will see that how you have to access this NGC, the latest version of the NGC catalog from the browser for your own work. And we in some of our lecture or maybe in this lecture or the next lecture, we will cover how to see the image of the NGC objects just for by 1 or 2 click. Then this NGC, the one example of a hot kind of NGC galaxy is NGC 4993, which is the 40 megaparsec away, where the first gravitational wave neutron star merger were detected in 2017. So you can see that the still NGC naming convention are widely used. In the 20th century, many catalogs were produced, such as the UJC catalog, RC3 catalog, etc. Nowadays, we are in the age of the automated digital service, such as DOPSS, DPOSS, SDSS, with the tens of hundreds, millions of galaxies we are being detected. They are labeled using unique ID. We will access in some of this lecture, we will access the SDSS database and see how the labeling in the SDSS is done. The large survey, like the current large survey like the Rubin or the Fuchsia survey or LSST, would provide the photometric information for about 10 to the power 10 galaxies from the local groups to the redshift of about greater than redshift 6, and this will provide us the useful measurements and the 6-band photometry for about 10 to the power 10 number of around 10 to the power 10 number of galaxies. So after making a census or the cataloging of the galaxy, you have to classify them based on some observable property, and this will be great for understanding how or why these galaxies are formed. So first, Hubble proposed a scheme for the classification of the galaxy. The Hubble's classification scheme is popularly known as the tuning fork diagram. This tuning fork diagram was first introduced in 1936 Hubble's book. The book's name was The Realm of the Nebulae. Still, the scheme survives in the essence to present day. In the scheme, there he introduced two types of galaxy. One type of galaxy is the late type galaxy. Another type is the galaxy is the early type galaxy. According to Hubble, the galaxies which had the spiral arm kind of thing, visible spiral kind of thing, they are the late type galaxy. And the galaxies which are the lenticular or the elliptical galaxy, he called them early type galaxy. There are different diverse types of galaxies. The galaxies are classified in the different types of the ellipticals, lenticular, spirals, irregulars. Those are the various types. A better approach may be to look at the properties of the kinematic subsystems within the galaxies, such as disks, spheroid, halos, etc., and deduce the origin of the galaxy and their evolution. So now here I have given example of the 4 different kind of galaxy, such as the elliptical, spiral, lenticular, and the irregular. You can see ellipticals are about the spherical kind of shape, spheroid kind of spheroid or ellipsoid kind of shape. This two is a spheroid and this is the ellipsoid. And the spiral galaxy have the observer for the spiral galaxy, you can see there are visible arms. In the arms there are the very bright spot in the spiral galaxy. This bright spot at the spots of the star formation, and also few spirals show this kind of spiral arm in the outside. And here in the central region there is a bird kind of formation. Those are named as the bird spiral galaxy. And few spiral there is a there is a fluorescent spiral. There are another type. Those are the another types of spiral. Those are also distinct from this two bird type or the visible type spiral. And next type of galaxy is the lenticular type of galaxy, where you can see a disc type of thing, and this bright small halo kind of feature. It is believed that some of these lenticulars are viewed not in the face on, but they are the edge on view of the galaxy, or maybe they are in between elliptical or spiral. Also, this kind of hypothesis is there. And the next kind of or the most fascinating kind of galaxies to us can be called the irregular galaxy. This irregular galaxies has no shape, so some of them has very good nickname. We will see in this lecture. And these irregular galaxies are often taken as a merger kind of system, because sometime you will see they are not a single galaxy. There are two different galaxy in the system of irregular. And one main thing to understand that the star formation also varies according to shape. Generally, for the elliptical galaxy, there is very less amount of star formation. In the spiral galaxy, you will see always a very high amount of star formation, and most star formation are ongoing on the arms. And for the irregular galaxy, you will see there are also very high amount of star formation and lenticulars are in between elliptical or spiral kind of star formation. So here is another different 9 kind of galaxy. One is a spiral, you can see that by shape. Another is elliptical, ellipsoid kind of shape. Next is the irregular kind of galaxy. Then it comes for the dwarf kind of galaxy. Then here is a ring kind of galaxy. Then is a starbust kind of galaxy. You can see another is a lenticular type of galaxy, ultra diffuse galaxy, and the interacting galaxy. This galaxy is known as the antenna galaxy. Sometime in this lecture we will introduce that antenna galaxy also. Now, what are the 3 main type of galaxy? So the spiral, elliptical, and the irregular, those are 3 main types of galaxy. The spiral galaxy, as the name suggests, there are the spiral arms. There are there are 3 distinct structure you can see in the spiral galaxy. One is the disc, another is the bulge around the center, and around is another is the halo, that is over the galaxy. The spiral galaxy, the bulge and the halo are the cooler have the cooler stars and few gas cloud, whereas the discs have the stars of all temperature and many gas clouds. So in the spiral galaxy, the disc is the place where the star formation is ongoing. As there is star formation is ongoing, there must have the supply for the star formation, supply fuel for the star formation. So the disc has the many gas cloud in the spiral galaxy. And for the bulge and the halo, mainly you will sometimes see the cooler star in the upper region of the disc thing. And there are star formation rate is very low in this bulge or halo, and so there are few gas clouds in the bulge or halo. Now, as we discussed, Dix is has the stars of all age and many gas cloud, and bulge contains the older stars and a few gas cloud. So in the Dix, you will find blue-white color, and which are due to the very young stars, very young bright stars that are the O-type, A-type stars, and the Dix stars are found to orbit in the plane in the same direction. In the bulge and halo, you will see some K-type, M-type stars. These are the red yellow stars because you know that they have cooler than our sun, about their surface temperature is about 3000 Kelvin, Kelvin or 4000 Kelvin. So this bulge stars are found to be rotated randomly around the Dix, and the spiral the bulge or halo stars orbit randomly around the Dix, or in the plane of Dix. There is a motion of the Dix stars. You can see here, this is the motion of the Dix star, and here there is a motion of the bulge star or the halo star. The next type of galaxies are the elliptical galaxy. They are spheroidal in shape, or the ellipsoid in shape. Virtually, they have no Dix or visually we can see they do not have any Dix component. Here is a typo. Little or no gas for the star formation. Generally, elliptical galaxies are believed to contain very little or no gas for star formation. But for some recent study, it is believed there are some evidence of some recent study that the elliptical galaxy also contain some amount of gas for star formation, but that gas is not efficient enough to form stars, and but that case we will not discuss here. So when we see the ellipticals, we first say that there are very less amount of star forming gas or there are very when we see the elliptical, we say that their star formation is very low, but maybe there is star formation very low, but this elliptical galaxies have the star formation fuel, but which is not efficiently forming stars, but that is the other case. Elliptical galaxies have low star formation rate. Vast majority of the elliptical galaxies are small, but there are few giant elliptical galaxies has been found. Elliptical galaxy has red or yellow color. So red and yellow color comes from the low mass stars. So the older stars. So the elliptical galaxies are the older have the older stellar population and little star formation. And in the elliptical galaxy, the orbit of the stars are also random. The next type of galaxies are the lenticular galaxy. So this galaxies are in between elliptical or spiral. The exact thing why this galaxy formed formed is not known, or this kind of galaxy has diverse kind of properties. Some properties are similar to elliptical, some properties are similar to spiral. One cannot distinctly classify it into elliptical or spiral group, so sometimes they are divided in another group. So this lenticular galaxies has a disc-like spiral galaxy, but much less dusty gas is present in lenticular galaxy. This lenticular galaxy contains no discernible this is an intermediate class between elliptical and spirals. Here is one example of the lenticular example of a lenticular galaxy. The next main type of galaxies are the irregular galaxies. This is neither spiral nor elliptical. It has irregular kind of shape. This elliptical galaxies has the blue-white color. Now this blue-white color comes from the stars with the comes from the galaxy constituents or the stars which are very high surface temperature, and you know that the young stars has very high surface temperature. They emit in the their blackbody spectrum peak at the UV or far infrared far infrared that region. So sorry, UV no UV X-ray that region. Yes. The irregular galaxy, for the irregular galaxy, their spectrum peaks near UV wavelength, and for irregular galaxies, the spectrum. Uh, Sorry for the delay. Irregular galaxies have the very high massive stars, which the stars have their spectrum peak in the UV frequency. So this bluish white color you can see if you observe in those irregular galaxy. Now this indicates that there must be young stars present in the system. So there is an ongoing star formation in the irregular galaxies. Now we will discuss few general facts about the galaxies which is seen from the observation. These facts there are many facts. We are discussing just a few. About 20% of the filled galaxies are found to be ellipticals, but most of the ellipticals are found in the clusters. There are a number of subtypes of elliptical galaxies such as the normal E-type galaxy, CD-type galaxy, thus as the massive bright ellipticals at the center of galaxy cluster, DE-type elliptical galaxy such as the dwarf elliptical galaxy, DSP H-type elliptical galaxy, that is dwarf spheroid type of elliptical galaxy. Those are extremely faint dwarf ellipticals, have small size, but they are the spherical or the spheroidal in shape. These galaxies are this dwarf spheroidal elliptical, dwarf spheroids you can say. They are usually smooth and almost featureless. This dwarf ellipticals contain no disks, no spiral arm, not any just lanes within these galaxies. Generally lacking this dwarf spheroidals lack on cold gas, hence few young blue stars are in those systems. Elliptical galaxies are often denoted with the En, that is where B by A is equals to, or the ellipticity, or B by A is equals to 1 minus n by 10. E4 galaxy has the axis ratio of B by A. B by A is the axis ratio B by A, and from if A and B is known to you, then you can find the eccentricity of the system or the eccentricity of the spheroid thing, the spheroid, and E0s have the circular isopods. Lenticulars are characterized by the presence of central bulge and a disc and the absence of any spiral arm, or that is the low or very little star formation ongoing within these lenticulars. They are taken as the intermediate class of galaxies, and they have the properties, some properties are there similar to ellipticals, and some properties of there is similar to spirals. Now the spirals are named for their bright spiral arms you can see, which are the prominent due to emission from the bright O or B type stars. And we know this A type and the O type or the B type stars die within 100 mega year. O type stars we found that they die within 10 mega year, or the B type stars die within 100 mega year. So there is evidence for the recent star formation. So if you find evidence of the O or B type star, you can say that the system had formed very late time star formation event happened in those system, and these spirals and also show the absorption due to dust lanes. roughly half of the disk galaxies, such as including our Milky Way. So, a central bar which is constituents which contains up to one third of the total light bar. This bar, this central bar feature are formed due to the dynamical instability of differentially rotated stellar disks. These central bursts are formed due to the dynamical instability of differentially rotating stellar disks. S0 type galaxy, that are S0 types of galaxy have no bar. A bar can persist in the even persist in the absence of gas. And bar patterns is not static. It is found that they rotate with a pattern speed. But unlike the spiral arms, they are not density waves. Stars in the bar stay in the bar. The asymmetric gravitational force of the disks allows the gas to lose angular momentum by shock and compressing the gas along the edge of bar. The gas loses energy and moves closer to the center of the galaxy. So this bar, why the bar forms in the this bar spiral galaxy is one of the hot topic of research. Also, so it is seen that the bar patterns are not static. Thus, bar rotate with with having a pattern speed, but those are not like any structure of the those are not like the structure of the spirals arm. Spiral arms are formed due to density wave in the disks. Stars in the bird stay in the bird. They do not move away from the bird, or they do not go to the halo or the bulge region. The asymmetric gravitational force in the disks allow the gas to lose the angular momentum, and the gas gets compressed along the edge of the bar. The gas now loses energy or the dissipates energy and moves closer to the center of the galaxy from the bar. So here are we discussed few observational facts about the different types of galaxy, such as the elliptical galaxies, spiral galaxies, bird spiral galaxies. And now we should see how what is the shape of our Milky Way. Our Milky Way is a bird spiral galaxy having a central bar-shaped structure and the well-defined spiral arms extending outward. Our galaxy is classified as the SB BC type galaxy, meaning that it has a moderate central bulge and loosely wound spiral arms. The main spiral arms of Milky Way are the Perseus spiral arm. Main spiral arms are the Perseus spiral arm. Then there is a Sagittarius spiral arm. There is Scutum Centaurus spiral arm. Another is the Carina spiral arm. Another is the Carina spiral arm. Another is the Norma spiral arm. And near our sun there is an Orion spiral arm. You can see the Orion arm, which is the Orion arm, a minor spur between the major arms, is where our solar system is located. You can see also in a figure there are a few larger arms and there are few minor arms here also, which get emitted from the major arms. So the major arms are the Scutum Centaurus arm. There are Sagittarius arm. Here is a long bird. There is the outer arm. So the main spiral arms are the Perseus arm, Sagittarius arm, Scutum Centaurus arm, and the Carina arms. And there the active star formation region contains young hot stars and also dust gas are present with those in these arms. The Orion arm, the minor spur between the major arms is where our solar system is located. This is about 27,000 light years away from the galaxy's center. Uh, as the core is of the Milky Way harbors a central supermassive black hole that is named as the Sagittarius A star, and it is believed that this galaxy, this central supermassive black hole, has about mass of 4 million times solar mass. Our galaxy spans about 100,000 light years in the diameter and contains about 100 billion stars, continuously evolving a star as the star swarms are forming and dying, and the dynamical structure of the spiral also gets changes over time. So until now we had discussed what are the galaxies. So galaxies are made up with three things. One is the gas, another is the star, another is the dark matter. So the gas is about the stars is about 10, the star is about 10, gas is about 1, and the dark matter is about 100. This is the average mass ratio for the constituents of galaxies. Now we have seen that the galaxies have the varying kind of based on morphology. First we classify the galaxies, and this galaxies are, according to morphology, galaxies are classified in the three categories, such as the spiral, another is the elliptical, and another is the irregular. The spiral galaxies have the higher star formation rate than elliptical, and the elliptical has very little star formation rate. Now the spiral has also the spiral arms are present in the spiral, but for the spiral arms are present, and the elliptical you can see there is no arm like structure. Ellipticals are featureless. No dust lane is the elliptical, you can see in the ellipticals, and also ellipticals are radar kind of color, so they contain radar kind of star. That's the very old star, K type, M type star. Those are very least massive stars also, and the spirals have the bluer color often in the photometry. When you do the photometry of these galaxies, the spiral, you can see the spiral galaxies have the bluer color. So the blue color comes from the bluer stars. That's the O type or E type stars, O type, B type, A type, those kind of stars. As those stars live for the least number of years, so we can just say that the spirals have the young stellar population. Between spiral and the ellipticals, there is a subtype of galaxy, you can say, or subclass of galaxy, that is a lenticular galaxy. Those have few properties of elliptical and few properties of spiral. And the next type of galaxy are the irregular galaxies. These irregular galaxies have the higher star formation, high star formation rate, you can say, and this structure is very loosely bound. Sometimes you can see there are collisional system. In the system there are two galaxies, and huge star formation rate is often seen for such system. So now we just discussed the names of few different kind of galaxy: the dwarf galaxy, ring galaxy, star-burst galaxy, ultra diffuse galaxy, interacting galaxy, lenticular galaxy. In the subsequent slides we will discussed that there are spiral galaxies has three different structure. One is disk, another is the central bulge, and another is the halo. So the disk contains the stars, all the stars, and the disk stars have the all temperature, can have all temperature mass distribution, and also the stellar disks contain high amount of star forming gas or the fuel for the star formation. And whereas the bulge or halo has very less number of stars or few gas cloud, and it has been seen that the bulge contains radar kind of star or the older kind of stars in the spiral galaxy. And the movement of stars of bulge and the disks are also different, and this bulge stars move in the random orbit. you can see around there is a disk. There is the bulb stars are moving in the very random orbit, in the chaotic orbit, you can say very loosely. And the spiral galaxy and the disks of the in the disk stars in spiral move in some good orbit. You can see there is some, they sometime go up the some distance of the disk, then come cross the disk and then go just below, then just come up, then just go below. This kind of wavy type of orbit they follow in the stellar disks. So the disk stars and the bulb stars, though those are also their movement or the orbit is different for spirals, and also their types are different. The disk stars are sometimes blue, the disk stars are bluish white color star mainly, and the bulb stars are mainly the redder star or redder star or the redder and low stars. The next type of galaxy, the elliptical galaxy. Ellipticals generally have the gas content is very low. Gas content is very low. On average, we told that their gas is to star is to dark matter is 1 is to 10 is to 100. But sometime for the elliptical, you will see the gas content is lower than the gas content or the gas content, and the star content is very low that the average. This is always the case. And for the elliptical galaxy, the star formation rate is very low. The star formation is very low, or there is no or little star formation, you can say. Sometimes they have contain fuel, but the fuel cannot efficiently form the stars. The vast majority are the small. The vast majority of ellipticals are the small in size, but there are few giant ellipticals. And another thing, the ellipticals are mainly redder or yellowish color. That is, they contain the stellar population, the older stellar population. And the ellipticals, the orbit of stars in the ellipticals are also random, just like the bulb stars. Just like the bulb stars orbit, what we see in the spiral galaxies. And between elliptical and the spiral, there is a lenticular galaxy which has a disk like spiral galaxy, but it do not contain contain very less number of dusty lens, and this do not contain any kind of feature, and this is intermediate between spiral and ellipticals. The next type of galaxies are the irregular galaxy. This is not neither spiral nor elliptical galaxies, but these galaxies are with the blue white color. So blue white color suggests there must be young hot ORB type stars. So this galaxy is star forming kind of a thing. This galaxy is star forming and ongoing star formation is present in these galaxies. Now we discussed few facts about galaxies, that ellipticals are only found in the clusters. Ellipticals are subdivided according to their B by A or the axis ratio sometimes, and also due to their properties. Ellipticals, there are different subtype of ellipticals such as the normal ellipticals, massive bright ellipticals, another is the dwarf elliptical, dwarf spheroidals, and usually the dwarf galaxies we are smooth and almost featureless, contain no disks, no arm, or no just length, and generally this dwarf do not have the cool gas. Then so the star formation of dwarf is also very low, and the young very young blue star, very blue color is very less for the dwarfs. And also there we discussed about the bird in the spiral galaxy, and we learned that the bird pattern in the spiral galaxies is not static, it rotates with a pattern speed. And the formation of bird and the formation of spiral, these two are different. We will not discuss this two in detail, but we just tell that the formation scenario of the spiralums and the bud is are different, or the formation mechanisms are different, for clearly saying. So and another thing, the stars in the bud stay in the bud. There is the gravitational force in the disks, in the any disks of the galaxy is asymmetric, and this allow the gas to lose the angular momentum, and this compresses the gas along the edge of the bud. Now this compressed gas lose their energy and moves the closer to the galaxy, and one can see the bar kind of structure. Now then we discussed we then discussed about our own Milky Way. So our own Milky Way has a main spiralum, and between main spiralum there are minor spur or the minor arms, you can say. The main spiral arms are the Perseus spiralum, Sagittarius spiralum, Scutum Centaurus spiralum, and the Carina spiralum. Those are the spiral arms are the region of the active star formation, and this spiral arms contain gas, dust, and also the young hot stars. The Orion spiral is this place where our Milky Way is located. This Orion spiral is you can see in between the Perseus and this long bar, this Scutum Centaurus. This is in between Perseus and the Scutum Centaurus. There is this minor spur. These are being originated from the major spurs, and this Orion spur is about 8 kiloparsec away from the galactic center. It is believed that the all galaxies have a central supermassive black hole where the very high mass, that is about 10 to the power 6 to 10 to the power 8 solar mass, is getting concentrated within the center of the galaxy. And just like that, our galaxy also harbors a central supermassive black hole, which is then as the Sagittarius A stars. Our black hole has been estimated to have a mass of 4 into 10 to the power 6 solar masses. This mass estimation of the central supermassive black hole is done by the movement of the stars near the central black hole, but we will not discuss that here. This is the mass mass has been measured with different techniques, and one great technique which received the Nobel Prize in the 2 or 3 years back is the by getting the motion by tracing the motion of the near center stars. And this galaxy, our galaxy spans approximately 100,000 light years in the diameter, and it is believed that our galaxy have around 10 to the power 11 number of stars, and the stars are continuously evolving and our galaxies the stars are continuously forming, so our galaxy is continuously evolving, and also the stars are dying. So there are some supernova events or the star formation and star die. This too determines what will be the dynamical structure of the spiral arms. The next thing we will discuss today is the Hubble's galaxy classification. So this Hubble's galaxy classification, you can see there are Hubble classified this galaxy in different types: ellipsoid galaxy, spheroidal galaxy, ellipsoid galaxy, spheroid galaxy, ellipsoid galaxy, spheroid galaxy. So he told that the galaxies are of two types. One is the spheroid dominated, and another is the disk dominated. So the spheroid dominated first kind of galaxies are the S0 kind of galaxy. S0 kind of galaxy. From S0 there is a two type of just like fork, there are two things are getting originated. One is the SA type, SB type, and the SC type, and the next another in the another branch there are galaxy which are known as SBA, SBB, and SBC. Spheroidal bulge A type, spheroidal bulge B type, spheroidal bulge C type. And another is the spheroidal A type, spheroidal B type, and spheroid C type. And another is the ellipsoid E5 and ellipsoid E0. That has this ellipsoid galaxies has the rounder appearance, and along this direction there is larger bulge, less dusty gash, and tighter spiral arms. In this way there is loosely spiral arm, and here is the lighter spiral arm and the less dusty gash. These are the disk dominated galaxies, and these are the spheroid dominated galaxies. So Hubble's tuning fork diagram provides a systematic way to study and classify galaxies based on their morphology, and this was the first such sequence of classifying galaxies according to the morphology, and this helped to differentiate between the different structure of the galaxies, and according to this structure the galaxies are early at this galaxies were classified. Hubble himself suggested that this sequence is an evolutionary sequence, and it was some of the astronomers hypothesized that the galaxies evolves from ellipticals to spiral, but it over time this hypothesis was proved wrong. This diagram highlights the main key thing of this diagram is that this diagram highlights the relationship between galaxy's shape, gas content, and the star formation activity, where the spiral galaxy or S0, the spiral type of galaxy, S0 is the spiral. Did I take any mistake? If I did any mistake, just forgive me. There is the S0 is the spiral type of galaxy, spiral A, B, C, and another is the ellipsoidal galaxy. S0 is the spheroidal galaxy. After spheroid, you will get the spiral galaxy. This spiral is SA, SB, SC, and the spiral bulge dominated galaxy, that is the SB, SBA, SBB, SBC, and along this way there is the loose, tighter spiral arm and higher rest. Now this diagram highlights the relationship between galaxy shape, gas content, and the star formation activity, with the spiral galaxy that are in the just two branch of this fork have more gas and ongoing star formation, whereas in the base of the fork you can say that in the base of the fork you can place the elliptical galaxies which are gas poor and contain older star. So thus Hubble tuning fork classification classifies the two type of galaxies such as elliptical or spheroidal according to their shape, and makes the elliptical or spirals are according to their shape or the visual shape property. So in the elliptical there are two types of galaxy. One is the ellipsoid type of galaxy, another is the spheroid type of galaxy. In the elliptical, the first type of galaxy in this galaxy is the S0 type of galaxy, and from the S0 type there are two branches being originated. S0 there is a spiral A, spiral B, spiral C, and another is the SB, SBB, and SBC. SBB, this is the spiral bulge dominated SB. And this and another type of galaxies are the elliptical galaxy, elliptical type 0, elliptical type 5, and S0 and SB0, these are the in between spiral or the elliptical shape, the S0 and SB0. So this diagram highlights the relationship between galaxy shape, gas content, and the star formation activity, where the spirals have more gas and ongoing star formation, while ellipticals are gas poor and contain older stars. This tuning fork diagram serves as a fundamental framework for the modern galaxy classification system and influence the studies of galaxy formation and evolution. While later research refined the understanding of the galaxy's evolution from the Hubble's idea very much, the diagram given by Hubble still remains the crucial tool for extragalactic astronomy. So, for your reference, I will say that Hubble differentiated galaxies in two types: S type or E type. S type or E type, that is the spiral type galaxy or the elliptical type galaxy. Spiral 0 is 0 type of galaxy at the spheroid kind of shape, have the spheroid kind of spiral S0 and SB0. Is 0 to SA, SB, SC, and another is the SB0, SB0 to SBA, SBB, and SBC. And this elliptical galaxy, this is the spheroid dominated galaxy, E5 to E0. S0 is the spiral galaxy. This is not spheroid. No, this is spheroid dominated. This is spheroid dominated. S0 is the spiral. Maybe yes, thank you for reminding. Maybe I told something wrong in this while I was discussing this slide before. S is the spiral and E is the elliptical. For the spiral, there are two types. One is the so that is the lowest level spiral, you can say S0 or SB0, and S0, from S0 there are SA, SB, SC. Those are S a spiral galaxy and E are the elliptical galaxy. And the spheroid dominated E0 is the most is the zero eccentricity or ellipticity. E0 is the spheroid kind of galaxy here. And SB0 is the spiral bulge dominated galaxy. Spiral bulge dominated galaxy. How the bulge, how big is the bulge, how big is the dusty lens, gas lens, or how the tighter the spiral arms are oriented. According to that, it is the types, subtypes are decided between spiral and elliptical. So, in the Hubble's tuning fork diagram, there are spiral types of galaxy and the elliptical types of galaxy. Spirals are classified in the two branch. One is the SA, SB, and SC branch, and another is the SB, spiral bulge dominated bulge branch, that is the SBA, SBB, and SBC. And another from this bunch, from this base, there is another branch is emerging, that are the elliptical galaxies. And the elliptical galaxies E5 to E0, those six type of galaxy. And E0 is the most rounder kind, spheroidal kind of appearance. E0 has the spheroidal kind of appearance, and along E5 to E0, the spheroid dominates. There are few galaxies which does not fit in the Hubble scheme, such as the galaxies with the irregular morphology. Those are classified as the irregular galaxies. The galaxies at very high redshift galaxies, and the galaxies which have the low surface brightness galaxies are almost galaxies, or they are sometimes known as the dwarf galaxies. Those do not those three types of galaxy do not fit in the Hubble scheme. Another thing to note, objects along the sequence are often referred as either early type galaxy or the late type galaxy. Early type galaxies are the elliptical galaxy, and the spiral type galaxies are the late type galaxy. Elliptical and the S0 type the galaxies, Hubble collectively called them early type, and the spiral galaxies he called the late type galaxy. Within spiral, SA galaxy is called the early type spiral, and SD is called the late type spiral. This nomenclature is not a statement of the evolutionary stage of object, but merely a nomenclature of purely historical origin. So you must have to understand that, or must have to keep in mind, that the object along this Hubble's sequence diagram are often called in the early type galaxy or the late type galaxy. Elliptical and the S0 type of galaxies are called the early type galaxies, as they're in the left figure, maybe in that sense we give the name. or there may be other sense, but this is a historical origin commonly. Ellipticals and the S0 types of galaxies are called in the early type galaxies, and the spirals are called spirals, or the galaxies with the arms arms are called the late type galaxy. Within spiral, the A type galaxy is called the early type spiral galaxy, and SD is called the late type spiral galaxy. So this nomenclature is completely a nomenclature of the due to the historical origin, and the Hubble gave that name, and this name has been going on since then. This is not regarding any this early type, late type. Often you will see those terms, but you must know in the mind this is not anything due to the evolutionary path of the galaxies. The morphological classification is at least partially affected by the projection effect. If, for instance, the spatial shape of the elliptical galaxy is of the triaxial spheroid, then the observed ellipticity will depend on the orientation with respect to the line of sight. Also, it will be difficult to identify a bird in the spiral that is observed from its side edge on. Similarly, a weak disk in a face on S0 is hard to spot. Around 30% of galaxies are redshift 1 are the peculiar galaxies. Galaxies are in the process of transformation. Generally, it is believed that the spiral galaxies form the elliptical galaxies. So, from the Hubble's diagram, the late type galaxy form the early type galaxy. This thing you have to keep in mind that this early type, late type, this is not the evolutionary thing. This is the thing of just purely history. In the latest stage of merger, two galaxies are no longer distinguishable. This product of the merger often look like some loosely bound system, irregular system, or irregular galaxies. Now we will introduce what are the dwarf galaxy. Now we will introduce what are the dwarf galaxies. Dwarf galaxies are the smaller galaxies which do not get included in the Hubble sequence due to their low surface brightness or low mass. This low surface brightness or the low luminosity is of this lower or often you will encounter this term, that is the dwarfs have the luminosity of about 10 to the power 6 to 10 to the power 10 solar luminosity, and it has mass of about 10 to the power 7 to 10 to the power 10 solar mass. That is and those are small in size, few kiloparsec, within 2 to 5 kiloparsec they are size thing, and they are mainly dark matter dominated. Their gas content or the star content is very low than average. Often low surface brightness, so they are hard to find. Objects are mostly gas poor. Passive DEDSPH, dwarf elliptical or dwarf spiral pH type of gas which star forming. Some dwarfs are often found to be some dwarfs are found to be the star forming dwarf. So also, why the dwarf galaxies are important? Majority of galaxies we detect in the local universe are the dwarf kind of galaxies. Dwarf galaxies may be the remnants of the galaxy formation process. The proto-dwarf gas clouds come together to form the larger galaxies. So, if you consider the hierarchical scenario of galaxy formation, then this dwarf galaxy can be one of the ingredient for formation of the larger galaxies. And these dwarf galaxies are currently, some dwarf galaxies are being cannibalized by the larger galaxies. One such example we will see in the subsequent slide, that how the dwarf galaxies are cannibalized, and if some dwarf galaxy is cannibalized, then what will be the system? It is believed that the system will be the larger galaxy will show some stellar stream, and one such Milky Way also shows such stellar stream. Dwarf galaxies are relatively simple system, not the merger product in some sense. They are pristine low metallicity galaxies. Dwarf galaxies, as we can detect dwarf galaxies in the nearby universe, so they can be a great tool for us to study how the galaxy formation happens in the later stage of for universe's formation history. We cannot do the far-field cosmology with them because we cannot measure those the greater than 1, greater than 2, that in that regime, but they can be a very good tool for doing the near field cosmology. The thing we discussed earlier, that the dwarf galaxies are being cannibalized by the larger galaxy. So if such event happen for our own Milky Way, we should see some of the trace of the dwarf galaxy around our Milky Way. Trace means some stellar stream or the star formation or the stream of gas around our Milky Way system. Using the Gaia satellite, such stellar streams has been discovered. Such stellar streams has been discovered. Now, this is one example of such a discovery of stellar stream with the Gaia data release 3. So you can find in the literature there is the Milky Way stream atlas. This the total number of 87 stellar streams has been discovered around the Milky Way. Typical mass is the 10 to the power 3 solar mass about. The longest stream is the longest stream is the Orphan Chenab stream, and the narrowest stream is C20 stream, and the streams with the Film Bluthal has the largest has the most number of stars within it. Largest galactocentric distance, or the largest distance, the stellar stream stream which lies is the Quando, and the closest to Earth there is stellar stream, that is the Nu 3 stellar stream. I have taken this stellar stream atlas figure, so that you can visualize that if some larger galaxy is cannibalized by the dwarf galaxy, then what will happen after the happen in the system. And also our Milky Way has the signature of such such event, that when our galaxy got cannibalized, one small galaxy got cannibalized by the gravity of our own Milky Way. It is believed that there was a dwarf galaxy known as the Sagittarius dwarf galaxy. Sagittarius dwarf galaxy. Sagittarius is the black hole at the Milky Way center. Sorry for any interruption. The Sagittarius dwarf galaxy has been orbiting the Milky Way for billions for the years. It is as it orbits around 10,000 more massive Milky Way. Gradually, it becomes colliding with the Milky Way's disks. The 3 known collisions between Sagittarius and Milky Way have triggered the major star formation episode, and one which may be given rise to the solar system. This is the one Sagittarius dwarf galaxy. It got attracted by our own Milky Way's potential, and and the stars from the systems got extracted, and the stellar streams got formed. Now, this was the Milky Way stellar streams. And why stellar streams are formed in our Milky Way. Now, one question in your mind is, do galaxies live alone? No, galaxies do not live alone. Galaxies are often live in group. Generally, spiral galaxies are often found in groups of galaxies, and the spiral groups are groups of galaxies up to contain a few dozen of galaxies per group. And the elliptical galaxies are much more mainly live in the huge cluster of galaxies, and this cluster of galaxies contain 100 to 1000 number of galaxies. So in the galaxy system, you will see there are two terms of regarding the system of galaxy, or the where the huge number of galaxies live. One is the galaxy group, and another are the galaxy cluster. Another is the galaxy cluster. So galaxy group contain about less than 100 number of galaxies, and this galaxy group mainly have the spiral kind of galaxies, and the elliptical galaxies are often a member of the galaxy cluster. Cluster is bigger than group, and clusters contain 100 or 2000 of galaxy, and most of them are the elliptical type of galaxy where no star formation. And we have seen that the elliptical galaxy do not have the ball-like shape or the arm-like shape, and the elliptical galaxy is devoid of the star formation. Elliptical galaxies are devoid of star formation, or they have very little star formation. And mainly elliptical galaxies, we now see they are the member of the huge cluster, and these huge clusters are of the contain 1000 or 100 about 1000 of galaxies. The next thing we will discuss about the example of few different type of galaxies. One such type of galaxy is the bird spiral type of galaxy. This bird spiral type of galaxy is NGC 1300. Here you can see there is a spiral arm at the outer region, and in the central region there is a bird kind of structure here. So NGC 1300 is a bird spiral type of galaxy. The next type of galaxy the lopsided spiral. This is known as this is a neighboring galaxy, such as galaxy is lopsided spiral. This is here the gravitationally the neighboring galaxy of it is gravitationally tugging on its disks of blue stars, pulling the stars in one of its side of the galaxy's outward and distort the galaxy's normal appearance. Here is the lopsided galaxy at the NGC 2276. It is believed that another nearby galaxy, that is NGC 2300, is gravitationally tugging the disks of this galaxy, and so that the outward the whole thing of the whole matter or the whole stars of this galaxy's disks are moving in the one-sided or becoming lopsided. So this NGC 2276, NGC 2300 system, we must see how this NGC 2276 and 2300 system looks in the Aladdin browser, or also we will see how to find different properties of galaxy using the NED website that we will see in the next class. Now we will discuss there are different variant of the galaxy. Different variant of the galaxy means we are saying that due to structure, just structure, we sometimes the galaxies give the galaxies a nickname. Another one such galaxy is shell galaxy. Shell galaxy are the elliptical galaxies which have the shell-like structure, which has never been observed in the spiral kind of galaxies. These galaxies, shell galaxies, are thought to be developed when a larger galaxy absorbs a smaller companion galaxy. That as the two galaxy centers approach, they start to oscillate around a central point, and the oscillation creates some gravitational ripples and the shells of the star formation, similar to the ripples spread in water. One such galaxy's example has been given. We will see few example of shell galaxy. Here the name of this galaxy I cannot remember, also I have not written here. This was my mistake. Of course we will see this shell galaxy. See this example and what are the shell galaxies and the shell galaxies image. We will download that in 2 or 3 different wavelength. The next type of galaxy is the spiral. We will discuss about the spiral galaxy or the grand design spiral galaxy. A grand design spiral galaxy is a type of spiral galaxy that is clearly defined with well organized spiral present within it. From the central bulge, so spiral arms are being emitted, you can see. These arms are maintained by density wave, which is triggering the star formation as the gas compresses along their path. Examples of such spirals are the M51 spiral galaxy, popularly known as Whirlpool Galaxy, M81 spiral galaxy. Both showcase the skirting symmetrical spirals. Grand design spirals tend to be more massive, more prominent structure of gives component, and the more bluer kind of color, because as there are more kind of spiral structure or the spiral arms, there are more formation of O or B type stars, so you will see the bluer color. The spiral arms are we know the spiral arms are a site of active star formation filled with the young bright star or nebulae or the star formation site. Another is the flocculent spiral. One such example of flocculent spiral is the NGC 2775. The flocculent spiral galaxy is a type of spiral galaxy with patchy and discontinuous spiral arm that appear to be fragmented. Unlike grand design spiral, their structure is not dominated by the well organized density wave, but instead formed by the local star formation and effect of the local turbulence due to the gas in the disk. This galaxy or this flocculent spiral triangle of galaxies often have more chaotic or fluffy appearance due to their irregular distribution of star formation region. Some of the Milky Way's outer structure exhibit some flocculent kind of characteristic, but if you want to view the flocculent spiral more great way, you have to see the galaxy that is the NGC 2775. Many flocculent spirals have the low mass and rich gas, continuing to star formation over the longer period. The next type of galaxy is the ring galaxy. We should discuss those. The ring galaxies have the ring, as the name suggests, ring-like appearance. Ring contains many massive, relatively young blue stars, which are extremely bright. The central region of the star, this galaxy contains relatively little luminous matter. Some astronomers believe that the ring galaxies are formed when a small galaxy passes through the center of a large galaxy. But why the ring galaxy? No, there is different hypotheses, and the exact answer why some galaxy will show ring-like appearance, whether it is there can be some outward, the galaxies is forming star in the outward, not forming star in the inward. In that case it show ring-like appearance. Also it can show ring-like appearance. So for the ring-like appearance of the galaxy there are different theory, but we see the many ring-like galaxies. Mainly the circular ring-like appearance, and the ring contains the massive young hot blue star. The young massive hot blue stars are contained in the ring. The next type of galaxy, the next galaxy we will discuss, the M82, that is named as the Seeger galaxy. This Seeger galaxy brightly shines in the infrared wavelength, and it is believed that it has a remarkable star formation activity. And the Seeger galaxies experience gravitational interaction with the galactic neighbor M81, and it is believed that due to the gravitational interaction, this Seeger galaxy or M82 is having the extraordinarily high star formation rate. In this figure, in the left figure, there is a Hubble image of the most detailed view of M82 ever captured. It isolates the galaxy from the glowing gas cloud while blocking much of the starlight. The image shows that the light is emitted by the sulfur, visible and ultraviolet light from oxygen and light from hydrogen. We will review this slide after 2 or 3 days. Sorry, after one or two lecture, and see what this different colors of this image tell. So M82, I have to just note that. Yes. Yes, I have to note, but you just, for now, you just keep in mind that M82 is known as the Seeger galaxy, and the Seeger galaxy is a starburst kind of galaxy, and here the starburst is believed to be happened due to gravitational interaction of the this galactic neighbor M81, and here is the M82 galaxy. And the next type of galaxy what we will discuss today is the Cutwell type of galaxy. As the name suggests, the Cutwell and its companion galaxies compositely imaged with the gems. You can see here the Cutwell galaxy image. In the recent JWST imaged the Cutwell and its companion with its NIRCam camera and the MIRI camera, which reveals the details that are difficult to see in the individual images alone. This image is formed as a result of high-speed collision. This galaxy is formed as a result of high-speed collision that occurred about 400 million years ago. The Cutwell is composed of the two ring, a bright inner ring and a colorful outer ring. A bright inner ring and a colorful outer ring. Both rings are expanding outward from the center of the collision like shock wave. So now, until now, we had discussed few popular galaxies such as one bird spiral galaxy, that is NGC 1300, a lopsided galaxy, a shell galaxy. We have not given the example of shell galaxy, but or the name of the shell galaxy, but we have only shown how the shell galaxy looks like. We will just discuss this galaxy or give the name in the next class. And we discussed the grand design spiral galaxy, that is M51. 51. Another is the flocculent spiral galaxy, ring galaxy. Ring galaxy's name also was not discussed here. Then I discussed about M82, that is the Seeger galaxy, and I will the star forming or the starburst galaxy. The M82 is a starburst galaxy. As the star formation is going on here, the main thing is the as the stars formation is going on very actively, you can say this type of this galaxy have star formation fuel, the fuel for the star formation. And also this galaxy have dust grains and just due to high amount of star formation fuel. As there is for actively forming stars, there are actively forming star means there are many O type or B type, those kind of high mass stars. These high mass stars emit UV photons. Now these UV photons get absorbed by the gas or dust in the galaxy, and this gas and dust emit in the infrared. So this galaxy have a very bright infrared emission. Such starburst kind of all galaxy have shown the infrared bright emission always, because that is the the de-emitted infrared emission we sometimes see in this starburst kind of galaxy. Also this starburst kind of galaxies has been imaged with the JWST and the HST for multiple times, and for the detailed view of the star formation sites, and this M82, due to its shape, just like a shape like Seeger, or this Seeger like shape, or the cylindrical Seeger like shape, this is known as a Seeger galaxy. And the Seeger galaxy have a companion that is known as M82. We will see that companion, and it is believed that the gravitational interaction of the companion just triggered the starburst, and this galaxy is actively forming stars now. Next type of galaxies we discussed at the Kuiper galaxy. This Kuiper galaxy have two rings. One is the central bright ring and another is the outer bright ring. Which is the outer bright ring is the very colorful than the central ring. So outer bright ring has many type of stars. This rings are expanding outward. Sometimes you can see that there are. Sometimes you can tell that there is a shock wave kind of thing is emitting from the center of the galaxy. So now this, any question? So today we will stop here at Kuiper galaxy. The next day we will show you some other few example of galaxies, and we will just check then the NED archive to know the different parameters of the galaxy, and this will be just like a demonstration kind of class, and we will just see how to derive information about galaxy in this course. You have any question? Do you have any question? If no, then thank you for joining. Thank you. We will start the next lecture from the comet galaxy. Thank you for joining.